Hello, everyone, and welcome to Aquaculture and Aquatic Animal Medicine. I'm MJ, and together with Mr. Alvin Stanio, let's talk about water quality management only here at VetMed 5298. Let's begin. So, at the end of this chapter, the student should be able to first recognize the effects of important water quality parameters on pond water and cultured stocks. Learn how to use water quality instruments and accurately interpret the recorded readings for each parameter. And lastly, to determine the optimum levels of water quality parameters necessary for culturing different aquaculture species. So, what is water quality? Water quality is the key to a successful fish culture operations. It composed of various physical and chemical factors, it plays a crucial role in maintaining a healthy aquatic environment for fish growth and survival. The most important water quality parameters include temperature, salinity, light, turbidity, and dissolved oxygen. Each of these affects fish growth and overall productivity. Chemical parameters such as pH, alkalinity, hardness, ammonia, nitrate, nitrite, carbon dioxide, hydrogen sulfide, and heavy metals must also be considered and monitored. All of these should remain within their optimum levels for thriving aquaculture systems. For gases, dissolved oxygen should be maintained above 4 to 5 parts per measure, while harmful gases like carbon dioxide and hydrogen sulfide must stay below lethal concentrations, especially in hatcheries. So, understanding and regularly testing these parameters help fish farmers maintaining water quality, ensuring healthy stocks, and maximizing production. So, let's talk about the first parameter, temperature. Temperature is the most important physical factor in aquaculture. It directly affects the growth, metabolism, and survival of fish and other aquatic organisms. Today, we'll be discussing how important the temperature and how it influences aquaculture and why maintaining stable water temperature is very significant. As temperature increases, fish metabolism speeds up. This means that they breathe faster and consume more oxygen. However, if the temperature rises too much, it can cause stress, leading to reduced growth and even death. Temperature also affects oxygen levels in water. Warmer water holds less dissolved oxygen, making it harder for fish to breathe. This is why proper aeration is essential in fish ponds. So, in ponds and lakes, temperature affects the stability of the water column. So, stability of the water column. Warm water stays at the top, while cooler water remains at the bottom. This layering is called thermal stratification. When the temperature drops below 4 degrees Celsius, the pattern reverses with warmer water sinking. Fish, plants, and shellfish all have an optimal temperature range for growth. For most species, the ideal range is 27 to 29 degrees Celsius, and within this range, growth is fast and efficient. Temperature also controls reproduction, and in this species like tilapia, spawning happens faster at 29 to 31 degrees Celsius. However, if the temperature falls below 21 degrees Celsius or rises above 35 degrees Celsius, it can lead to stress, disease, and even mortality. Abrupt temperature changes, especially more than 5 degrees Celsius, can be stressful for fish. That's why monitoring and maintaining stable water temperatures is critical for successful aquaculture. So, water temperature rises due to several factors. The three main contributors are first, dissolved substances. Minerals and salt retain heat, causing water to warm up faster. Next is the suspended particulate matter. Silt and debris absorb sunlight, increasing temperature. Lastly, the plankton. Large plankton populations trap heat, raising water temperature. So, for example, set up in fish pond, The water temperature at the surface is equal to 31 degrees Celsius, so before the start of a bloom of plankton, and becomes 35 degrees Celsius at the height of a bloom based on an observation. From this fact, it could be generalized that the greater the density of plankton, the more light is absorbed at the surface, and consequently, much heat is generated in the aquatic environment. So next, the salinity. Another parameter is the salinity, and it refers to the total concentration of dissolved salts in water measured in grams per kilogram. So when we talk about salinity, this is not just sodium chloride. While sodium chloride make up most of the salt content, salinity also includes potassium, magnesium, calcium, and sulfate ions, along with other trace salts. Maintaining the right salinity levels is essential for a balanced aquatic environment. So, aside from grams per kilogram, salinity is also expressed in various units or ways as follows: ppt or parts per thousand, percent or percentage. For example, is seawater is about 35 ppt or parts per thousand, or 35% or 3.5% salinity. So let's talk about the various techniques or methods in measuring salinity. First one is the density technique. This is considered as the least expensive. So recorded density is converted to salinity by employing conversion table. So for example, the instrument used to measure density is hydrometer. The next one is refractive index of seawater method, also considered as the simplest and most rapid method. It directly measures the salinity of the water through using the instrument called refractometer, which is quite expensive. Next is conductivity method. So this is considered as the method of high precision. This is more expensive and yet requires a fairly large sample and often useful for researchers than aquaculturists. Next is the titration method. Requires reagent solutions or chemicals and is done in the laboratory with the aid of burette, Erlenmeyer flask, and other laboratory equipments. So the first two methods above are to be used when salinity is suspected to be high. For example, more than or equal to zero point 0.5 parts per thousand salinity. So let's classify the aquatic environment on the basis of salinity. So fresh water should have at least or less than zero point 0.5 parts per thousand salinity. Brackish water, zero point 0.5 to 34 parts per thousand salinity. And lastly, marine water, more than or equal to 35 parts per thousand to less than 40 ppt salinity. So salinity in marine coastal waters is influenced by several factors. Two factors or major factors are first, the rainfall. Rainfall directly and indirectly reduces salinity of coastal marine water. So next one is the freshwater runoff. So freshwater runoff from rivers greatly reduces the salinity of the coastal marine water. And so culture sites should not be immediately adjacent to the mouth of the river. Let's talk about the effects of salinity. It affects the solubility of oxygen. So the dissolved oxygen, which I will be tackled later, decreases with increasing salinity and vice versa. It affects the osmoregulatory function of most aquatic vertebrates, including fish. So osmoregulation requires a significant amount of energy to maintain the fish body fluids to counteract with the effect of salt concentration of the habitat that may lead to mortality. Fluctuating salinity, especially a sudden change, such as decrease or increase of at least 5 parts per thousand salinity, greatly causes stress or even death of the fishes or other species. So another parameter is the light. Light is a form of radiant energy with the sun at its ultimate source. Its absorption in water depends on the angle at which it enters. So first is the lower angles, 1 to 45 degree angle. More light is scattered and reflected, reducing the absorption. So other one is the higher angle, around 70 to 90 degree. The light penetrates deeper, increasing absorption and warming the water. So in the Philippine setup, from March to November, more light is absorbed, boosting phytoplankton and algae growth. However, during November to March, less absorption leads to cooler waters. So let's talk about light and fertilization. Phytoplankton responds faster or more quickly to inorganic fertilizer when light absorption is high. So what are the functions of light? It supplies energy necessary for the primary productivity. So for example, production of all kinds of plants except fungi. For food of animal organisms, and the process involved in the primary productivity is also known as photosynthesis. Another one is illumination. It helps aquatic animals to see and find food. And another one is the food availability. It determines the type of and amounts of food available for fish. So another functions is the body coloration of this animal. It influences the pigmentation of aquatic animals. It also functions in the activity of some organisms. It directs and triggers the movement of aquatic species. Light absorption and penetration in aquatic systems are influenced by several factors. The deeper the light reaches, the more it supports aquatic life. So the key factors are dissolved substances, such as minerals and organic matter absorb light, reducing penetration. Another one is suspended solids, particulate matter particulate matter. Silt and debris scatters and block light, limiting depth reach. Lastly, plankton. Large population of plankton absorb light, affecting deeper zones. Another parameter we're going to talk about is the turbidity. It refers to the reduction of water transparency due to the dissolved substances, suspended solids, and plankton. So several factors contribute to the turbidity. This includes soil erosion, mining waste, sewage discharge, and another one is microbial breakdown of organic matter. And lastly, the planktons or plankton, such as phytoplankton and zooplankton. So let's talk about the effects of turbidity. First one, it limits the light penetration. It reduces photosynthesis and plankton reproduction. So another one is the damage it produces on the gills of the fish. And this can cause stress and respiratory issues in aquatic animals. Another one is the smoothers fish eggs and benthic organism, affects reproduction and ecosystem balance. Another one is phytoplankton die-off. It reduces food availability in the water. So next is the dissolved oxygen depletion. It leads to poor water quality. It also makes feeding difficult. So fishes struggle to find or locate food. Sedimentation affects pond bottom conditions. Lastly, clogging of hatchery pumps, filters, and pipelines causes operational issues in aquaculture system. So clay turbidity in ponds and tanks can be managed using several effective methods. The following remedial measures help clear the water without harming aquatic life. So the application of gypsum. So applying gypsum 20 milligrams per liter or 20 parts per measure can reduce turbidity by 91% safely. Another one is the application of agricultural lime, around 500 to 600 kilograms per HA, helps precipitate suspended solids, improving water quality. Lastly, the rice hay, application of rice hay around 500 kJ per HA effectively reduces turbidity by promoting particle settling. So turbidity is measured either by the following instruments and devices. First is the turbidimeter. It's expressed in parts per measure or ppm. For example, muddy waters usually contain less than 2000 ppm and clay turbidity in natural waters rarely exceeds 20,000 ppm. Next one is the Seki disc, a circular metal or wooden device, just like in this presentation. Um, Wooden device painted alternatively black and white attached to the graduated pole or rope, as you can see there, is expressed in linear measurement. For example, cm or centimeter or meter. This device measures the transparency of water or the distance of visibility of the Sekai disc from the water surface, measures the turbidity of such water. However, if turbidity is referred to as the abundance of plankton production, then the distance of the visibility of Sekai disc multiplied by 2 is equal to the depth of euphotic zone, the production zone. In fish pond, the depth of measurement or thickness of euphotic zone is usually less than 1 meter. Next one is the weighing balance. This device is used to weigh precipitates in milligram, gram, or kilogram, obtained from settling down the suspended solids or particulate matters. So another parameter we're going to talk about is the DO or dissolved oxygen. It is the most critical gas in fish culture, directly affecting fish health and water quality. So understanding DO dynamics is essential for effective aquaculture management. So what are the uses of dissolved oxygen in aquaculture? First, it is used for respiration. So it is essential for fish survival. Another one is for digestion and assimilation, as this improves feed consumption and nutrient absorption. Another one is the osmotic balance through helping to maintain internal stability in fish. Another one is to fish is to help the fish activity, supports swimming and food searching. Lastly, the oxidation of metabolites. It converts ammonia into nitrate and hydrogen sulfide into sulfate, reducing toxicity. So let's talk about the factors influencing oxygen production. First one is the light availability. The more light leads to higher photosynthesis. Another one is the chlorophyll bearing plants. So green plants contribute to oxygen production. Another one is nutrient concentration, as this supports plant growth and affecting oxygen levels. Lastly, the temperature. At near freezing or above 40 degrees Celsius, photosynthesis stops, reducing oxygen levels. So, dissolved oxygen levels can decline due to various factors affecting fish health and aquaculture productivity. So, first one is the high temperature. Warm water holds less oxygen, and high salinity, more saline water retains less oxygen, and high altitude, less atmospheric pressure reduces DO levels. So let's talk about why or what causes low DO levels. So cloudy or prolonged rainy weather, so that may result to less sunlight, reduces photosynthesis. Another one is plankton die-offs. Decomposing plankton consumed oxygen. Another one is heavy stocking and overfeeding. It increases oxygen demand. And high organic load. High organic loads decomposition depletes oxygen. So the signs of dissolved oxygen deficiency in fish. So this includes loss of appetite and sluggish behavior, gasping for air at the surface, gathering near water inflow. It also shows signs of slow growth, and lastly, increased disease and parasite outbreaks. So let's talk about the management of dissolved oxygen techniques. First is to monitor DO levels, especially at dawn or 6 a.m. You should also avoid overstocking and overfeeding. Use a sliding feeding rule or gradual reduction. Another one is to prevent over-fertilization in ponds. Lastly, use aeration and water circulation system. So let's talk about another parameter. The pH. pH is actually a crucial parameter in aquaculture, measuring the degree of acidity or alkalinity in water. It does not indicate total acidity or alkalinity, but rather the intensity of these properties. So, what is pH? So, pH is expresses the hydrogen ion concentration in water. So, the term pH stands for power of hydrogen. So, power of hydrogen. So, P is equal to power and H is equal to hydrogen. So, how does pH works? Acidic solutions. So it releases hydrogen ions if low pH. So basic solutions, it absorbs hydrogen ions at high pH. So mathematical calculation, the hydrogen ion concentrations can be derived from pH values, helping in water quality assessment. So the importance of pH in aquaculture. The vital factor in water quality, it is a vital factor in water quality, influencing fish health and overall aquatic balance. So let's talk about the scale of the pH. So it ranges from 0 to 14, where pH 7 is neutral, equal balance of hydrogen ion donors and acceptors. So if we have less than 7 pH or pH less than 7, it is considered as acidic. So more hydrogen ions. If pH is more than 7, it is basically basic or alkaline. Fewer hydrogen ions. And the farther from 7, the stronger the acidity or alkalinity. So let's talk about the pH variation in natural waters. It is higher during the day due to carbon dioxide absorption by phytoplankton during photosynthesis. It is lower at night because carbon dioxide of the buildup of carbon dioxide from respiration and it increases acidity. So let's talk about monitoring and ideal pH levels. So you should check pH and daybreak and afternoon to track daily fluctuations. Best pH for fish production is 6.5 to 9 at daybreak. So at pH 4 to 6, we can notice some signs of slow growth. And below pH 4 or above pH 11, this can potentially lead to mortality. So let's talk about the alkalinity, another parameter in water quality management. So alkalinity plays a crucial role in maintaining water quality by neutralizing acid and ensuring a stable environment for aquatic life. So basically, what is alkalinity? It is the ability to accept ions, hydrogen ions, or to neutralize acid. It is the counterpart of acidity, and it is measured by a milligram per liter or ppm or parchment measure of calcium carbonate. Sources of alkalinity in natural waters. Carbonate and bicarbonate ions are the main contributors. So what are the types of alkalinity producing compounds? So compounds producing only alkalinity, for example, sodium carbonate, sodium bicarbonate, um, potassium carbonate, potassium bicarbonate. So another one is the compounds producing both alkalinity and hardness. For example, calcium carbonate, calcium bicarbonate, magnesium carbonate, and magnesium bicarbonate. So why we need to express alkalinity in terms of the calcium carbonate? So it simplifies calculations and standardizes procedures, link alkalinity with water hardness, and some compounds contribute to both. So let's talk about alkalinity and carbon dioxide relationship. So carbon dioxide dissolves in water and it forms carbonic acid. Alkalinity influences carbon dioxide availability for phytoplankton, which is vital for photosynthesis and aquatic productivity. So pH and alkalinity plays a critical role in water chemistry, especially in regulating the availability of carbon compounds and supporting aquatic life. Um, in terms of pH and carbon compound reactions, if we have an increase in pH, it shifts the reaction to the right. Meanwhile, the decrease in pH shifts the reaction to the left. So at pH more than 4.5, dissociates into um, bicarbonate. So again, at pH more than 4.5, the hydrogen carbonate dissociates into bicarbonate. And at pH 8.3, more than 8.3, bicarbonate transforms into carbonate. So during the day with higher pH, carbon is available as hydrogen carbonate, carbon dioxide, CO3, and hydrogen carbonate. So at night, pH drops due to the carbon dioxide production. So in terms of alkalinity and carbon dioxide availability, so alkalinity less than 20 milligrams per liter, it produces limited carbon dioxide for plankton production. Alkalinity around the range of 20 to 150 milligrams per liter produces sufficient carbon dioxide for plankton production, and it is ideal for fish culture. So when we have low alkalinity, fish are more sensitive to toxic pollutants. So to measure the levels of alkalinity, it is measured by titration or using a hack kit. So optimum total alkalinity range is 20 to 300 milligrams per liter. So balancing pH and alkalinity ensures a healthy aquatic system, providing a stable environment for fish culture and promoting plankton production.
So good day everyone, my name is Alvin J. Estaño and I will be reporting the remaining water quality parameters and their importance in aquaculture as well as the best practices for pond and cage management. So we have here hardness, ammonia, nitrate, carbon dioxide, hydrogen sulfide, and heavy metals. For the total hardness, it measures the concentration of divalent cations, mainly the calcium ions, and magnesium. These minerals are essential for fish development and shell formation in crustaceans. The hardness level is expressed as mg per L of calcium carbonate. So there are types of hardness in water. First, we have the temporary hardness. It is caused by calcium and magnesium bicarbonates. This can be removed by boiling the water, which converts bicarbonates into insoluble carbonates, leading to precipitation. Permanent hardness, on the other hand, is caused by calcium sulfate and other inorganic salts. This type cannot be removed by boiling and requires chemical treatment. So for the recommended range, we have 20 to 300 mg per L of calcium carbonate. So water with temporary hardness are said to be soft waters, while the water with permanent hardness are called hard water. The total hardness is measured by titration method or by reagent chemicals with the use of hatch kit. Why is hardness important? It is essential for fish bone development and muscle function. It influences the pH stability by buffering the acids, and it helps as well to reduce the toxicity of certain heavy metals. Ammonia is the second most critical gas in fish culture, next to oxygen. It is produced from fish wastes, uneaten feed, and organic matter decomposition. High ammonia levels are toxic to fish and can cause gill damage, making it difficult for fish to breathe, stress and weakened immune systems, leading to disease outbreaks, reduced growth rates, and poor feed conversion effects. Increase in ammonia level is actually caused by first is overfeeding, second is protein-rich feed, and excess food decay. As long as the pH is 8 or lower, the NH3 levels of up to zero point 0.5 parts per million will be safe. The free ammonia or the NH3 is actually toxic and harmful to fish, while the NH4 plus or the ammonium ion is less toxic and it is safe at low pH levels. So for the safe ammonia levels, we have the NH3 is equals to lesser than zero point 0.1 ppm as NH3N. For NH4 plus or the ammonium ion, we have less than 1.5 ppm as NH4 nitrogen. For the total ammonia or the NH3 plus the NH4 ion is equal to 1 to 2.5 parts per million. So how do we control ammonia? Regular water exchange to dilute ammonia levels is first. Second is to reduce overfeeding to minimize the waste. Third is to use biofilters like nitrifying bacteria to convert ammonia into less toxic nitrates. Nitrites are an intermediate product in the nitrogen cycle formed by the oxidation of ammonia by the Nitrosomonas bacteria. Although less toxic than ammonia, nitrites still pose a threat to fish by interfering with oxygen transport in the blood, leading to a condition known as the brown blood disease or methemoglobinemia. So the formation of nitrites, we have the aerobic conditions, we have the partial oxidation of the ammonia. Then for the anaerobic conditions, we have the reduction of nitrates by denitrifying bacteria. So in the present, its presence as water is found in low concentrations due to rapid oxidation to nitrates, and the recommended limit should not exceed zero point 0.1 parts per million of NO2 nitrogen for hatchery purposes. So how do we control the nitrites? We have to improve first the aeration to enhance oxidation of nitrites to nitrates. Second, we have to increase water circulation to prevent accumulation. And then, maintain a healthy nitrifying bacterial population in the biofilters. For the nitrates, nitrates are the final oxidized form of nitrogen and are less toxic than ammonia and nitrites. However, excessive nitrates can lead to eutrophication or the overgrowth of algae that depletes dissolved oxygen and negatively impact the water quality. So for the aerobic conditions, the formation of the nitrates, we have the oxidation of nitrites by, of course, the Nitrobacter bacteria. And for the external sources, for the formation of nitrates, we have the chemical fertilizers like urea and industrial wastewaters and agricultural runoff. So the presence of the nitrates in the water is commonly found as the fully oxidized form of nitrogen, as what I have said earlier, and the recommended limit should not exceed to 100 parts per million of NO3 nitrogen. So how do we control nitrates? So we have to conduct partial water changes to remove the excess nitrates. We have to also to use we also have to use live plants or biofilters to absorb nitrates. We have to avoid excessive fertilizer runoff from the nearby agricultural areas. Here is a table summarizing the difference between the nitrates and the nitrites. So for the oxidation state, we have the nitrite as partially oxidized, while the nitrate is fully oxidized. In the formation, the nitrite is actually formed from ammonia by the Nitrosomonas or the aerobic bacteria, or from nitrates by denitrifying bacteria. For the nitrates, on the other hand, it is commonly found it is formed from the nitrite. It is formed from nitrite by the Nitrobacter bacteria. So the presence in water for nitrite, it is usually in low concentrations due to quick oxidation, while the nitrates, it is commonly found in water and from other external sources. So for nitrites, the external sources, it is limited. The external source is limited only. The accumulation is limited only in the water, while for nitrate, it comes from fertilizers, industrial wastewaters, and agricultural runoff. And then for its toxicity, For nitrite, it is more toxic to aquatic life. So, however, for nitrates, it is less toxic, but it can cause issues at higher levels. For the recommended limit, we have lesser than or equal to zero point 0.1 parts per million for the hatchery for nitrites, and then for nitrates we have less than or equal to 100 ppm per NO3N. Carbon dioxide, or CO2, is naturally present in water due to respiration from the aquatic organisms and decomposition of organic matter. So, high CO2 levels can cause respiratory stress to the fish, making it harder for fish to extract oxygen. So, pH fluctuation also, which can lead to stress and disease. So, carbon dioxides are consumed by the plants during the day, producing oxygen. It is inversely related to dissolved oxygen. So if there is high CO2 or carbon dioxide, there will be low dissolved oxygen. If there is high carbon dioxide, it means that there is poor photosynthesis in the aquatic environment. And then if there is low carbon dioxide, meaning the photosynthesis is optimized. For the aeration, aeration adds dissolved oxygen and removes excess carbon dioxide and ammonia. For the limit, we have lesser than or equal to 10 ppm of carbon dioxide. For hydrogen sulfide, or H2S, it is a highly toxic gas produced under anaerobic or oxygen poor conditions, often in pond sediments. Even at very low concentrations, it can cause fish mortality. So, hydrogen sulfide no, is a product of decomposition of sulfur compounds in sediments under anaerobic conditions. So, the safe levels or the limit for the hydrogen sulfide, it should not exceed to zero point 0.1 parts per billion. How do we prevent the hydrogen sulfide buildup? So first, we have to avoid excessive organic matter accumulation. Second is to regularly steer the pond bottom to introduce oxygen, and then use aeration and water exchange to remove trapped gas. Heavy metals. Heavy metals can enter the aquaculture systems through pollution, industrial waste, and agricultural runoff. So, high levels of these metals can actually cause growth retardation, gill damage, and mortality in fishes. So, in case that heavy metals are present in the aquaculture system, they should be at the limits or levels lower than presented below as follows. So for copper, we have 0.006 ppm, for lead 0.03 ppm, for cadmium we have 0.003 ppm, for mercury 0.002 ppm, for nickel 0.1 ppm, for zinc we have 0.05 ppm, for chromium we have 0.1 ppm, for iron 0.5 ppm, for manganese, we have 0.01 ppm, and then the polychlorinated biphenyls, or the PCB3, 0.002 ppm. So in this picture, all the red squares in the periodic table of elements are all heavy metals. Now that all the parameters for the water quality were all discussed, so let's proceed with the pond management. So, in pond management practices, the regular water exchange, it should be changed. The water should be changed 25 to 30% of the pond water during the spring tides. So we have to maintain the water depth for milkfish to 50 to 75 centimeters, while for shrimp and tilapia ponds, we have 80 to 120 centimeters. We have to fertilize after the last water exchange to maximize nutrient efficiency. We have to check the dikes, the gates, and the leakages regularly to prevent water loss. We have to use pumps when tidal current is low, and then we have to check and repair leaks, seepages, and gate screens, and we have to monitor stock health and address diseases immediately. For the cage or the pen management, we have to monitor the water quality the dissolved oxygen, the temperature, the pH, and the ammonia, the nitrite, and the turbidity. We all have to take into consideration these parameters. Then for the dissolved oxygen and temperature, these are the most critical parameters for cage and pen management. And then we have to monitor daily at key times, at dawn, at midday, at late afternoon, in the slack tide. And then lastly, essential for intensive farms with high production. So management of this cage or pen is very essential in intensive farms. So, in summary, water quality monitoring and proper pond cage management are essential for sustainable aquaculture. By controlling key parameters such as the ammonia, the nitrites, dissolved oxygen, the pH, and etc., we can create an optimal environment that promotes healthy fish growth, high survival rates, and improved productivity. So that concludes my presentation. I hope you have learned something, and thank you so much for listening.